So, like I announced on the ELO and like I announced last week, or maybe even more than once, we're going to try and prove the consistency of axiom of choice and GCH with ZF. That means that many times I will have to tell you we don't use AC anymore because we want to prove it in the class that we're talking about. We will use AC every now and then just to make some argument plausible, and then later we'll actually prove it without AC. But okay, that should be a boldface L in most books, but we're going to define a universe of sets called L, already by Gödel in 1940 when he wrote down his proof of the consistency of choice and GCH. And how did he do that? Well, how do you prove consistency of anything? You build a model. That is how mathematical logic works. Now, sort of the conceptual problem that you have when you do group theory, a model of group theory is a group. And after first year algebra, everybody here thinks they know what a group is, so fine. And they probably do, but... you know that I don't. Second year algebra then. And if we talk about fields or vector spaces or whatever, any sensible theory that you may have come across in your studies, the models of those theories were the exact subjects of study in those courses. Okay, now we do set theory. And so what on earth is a model of set theory? Well, that should be a set. Conceivably, well, maybe a class. Okay, what's that? Do we have any? Well, we have one. This one. I forgot, did I use on or ord when I... On. Okay, well, I have to... When you look at my notes, you will see that I switched to ord. Never mind. So this is... No, we started out simply by assuming that ZF was consistent. And our idea was, well, all those axioms seem reasonable. So why should they not be consistent? And the model we have in mind is simply the universe of sets. Whatever that may be. Well, those are all the x's that satisfy x equal x in our theory. Okay, but we don't know, what do we know about V? Well, that it's built up like that, and that's about it. We do not know how the continuum function works. We only have those statements that I made, if it behaves like this up to that, then you will get that behavior the next few steps. But no definitive answer saying, well, it behaves like that. So if we want to prove any consistency, V is useless because we don't know anything about it. Okay, so then where does the model come from? Well, this is going to be it. And what is it going to be? Well, here is V. And V has a backbone, that's the ordinals. And so what did we do? What did we do when we built V? We didn't care. We just took the power set of everything we had before. without any thought. Power set, power set, power set, power set, and that was it. What we'll be doing the next 4 weeks is we're going to build another hierarchy that potentially is much thinner than V, because we are not going to take all the power sets at once at the next step, but we're going to take a few well-chosen subsets of what we did thus far. Well-chosen means that we can describe them, that we can actually write down a definition for them. This doesn't guarantee anything, by the way. It just means that we're going to be more careful. And the idea is that if you are careful enough, you may be able to somehow do this choosing so carefully that you get a well-ordered collection. I'm not guaranteeing it, so maybe by doing this very carefully, we could well order the whole universe, L. Why not? Because everything is constructed step by step, and we can keep track of the steps using the ordinals, possibly. Okay, after that was the solution to that exam question, but and yes, that was me pulling your leg, Paul. So the thing we're going to do is do this very carefully, so carefully that we will be able to well order the whole universe L. Automatically, we will have well ordered all the members of L because L is going to be transitive. So then we have established that apparently the axiom of choice holds there. Almost. There are some difficulties. I'll come back to that in a moment. And the next thing is, if we take only really the minimum necessary amount of subsets to make ZF work, well, quite possibly we get GCH because we take so very few subsets of every set that we're taking. Maybe just taking the necessary subsets will automatically give us the generalized continuum hypothesis. So for example, we have at one point, we will have, of course, at level, one of the things that is going to happen is just like in the case of the V, every ordinal occurs in the L with the index +1. That's going to happen. So omega is going to be a member of L omega, so it's a subset. It's a member of L omega +1, it's a subset of L omega. That's one thing that we'll be seeing today. And like I said, if we're being careful enough, then maybe just maybe we can get this. And why would that be useful? Because we might also be able to get if we are very careful, very thrifty, stingy, I would almost say, if we are very careful constructing our new sets, then we don't add too many all the time. If we add these two things together, then suddenly the power set of omega has cardinality L of 1. Okay, so far that's only wishful thinking because we haven't done any construction yet. But this is what is going to happen. And I looked in my notes of a few years ago, and it turned out that somehow I managed to do this in 2 weeks, but I think I prepared a few things in advance. So I think we'll be able to do this in the next 4 weeks, maybe even a bit faster, and then I can give some examples of what happens in L that give other consistency results too. But this is what is going to what's going to happen. We're going to do this, but with greater care. No arbitrary, just whole power set. No, a very carefully chosen piece of what we think the power set is. And how does that work? I'm going to do it in steps. I'm going to make things more and more difficult first. First is definability. Because I said we're going to make L alpha plus 1 the def of L alpha. Well, that's all fine and dandy, but what does that mean? Well, we're going to take the definable subsets. Okay, fine. What does definable mean? And in Kunin's book, there is a chapter called Defining Definability. Yes, he was a funny guy, Ken was. But that's a serious joke, so to speak. You have to really make clear what you mean by definable. So before we can do definability, we have to define relativation. I think we did that, but I'm going to do it anyway again, just to be sure. M can be any, for now it can be any set. Most of the time it will be transitive, by the way. But there are a few moments where we also meet non-transitive sets. So this is going to be a useful, or even a class, by the way. It could even be a whole class. So I think we did that. I think we needed this at one point, and I already mentioned this, but never mind. Relativizing the membership relation means just keeping the membership relation. But we're going to do this the correct way. When we take the conjunction, disjunction, implication, bi-equivalence, or whatever symbols we might want to define, we just, we use a distributive law, so to speak. We distribute the m over the phi and the psi, and we just leave the connective as it is. And of course, the same thing. We do the same thing with the negation. Well, so far, we haven't done anything, because with all the formulas that we have done this, phi m was always phi, and psi m was always psi, so yes, but When we have an existential quantifier, we restrict it to m, and of course, we do. So what does the relativation mean? All the quantifiers get restricted. All unrestricted quantifiers get restricted anyway, but by m. I mean, there will be quantifiers that are restricted simply by other elements, and then we don't do anything. But if they're unrestricted, like these two, then we're going to restrict them by m. Lovely. That is the relativation. And so we could relativize to the universe V, but then we simply get phi back, because we assume the axiom of foundation, so V really is that iterated hierarchy for us from now on. Okay, this is not an important thing. Okay, so that's relativation, fine. And now comes the definition that we mean if there is a formula with some free variables, because we want to be able to insert things for the variables. So we have one variable u, and that's going to be the special one, and we're having a few other variables. There is a formula, and maybe I'll call this k. It's a whole mouthful. You have to digest it a little bit. So when do we call something definable? Well, when we can describe it, define it using a formula, and a few, finitely many, parameters from the set. So we are allowed to use some individual members of M to define further things. Not necessarily, but we can.
I'm sorry, in which universe do these formulas now live? We have a model of set theory in which we're defining these sets and the formulas?
All this takes place in V.
Okay.
So we are working in V all the time. And so M, okay, M could be one of two things. It could be just a set. Well, then this all makes sense. And then this is going to be a reasonable definition.
Yeah, because it seems like we're sort of quantifying over formulas, which seems a bit scary.
Okay, there goes my preparation, but you're right.
Ignore my question if you're coming back to it later.
Yes, I was going to make a whole thing of it later on, but you just spoiled the show. You're right. But okay, this is going to be sort of the intuitive first approximation of L. because the real work is in making this precise. But what I want to show, what I want to make at least plausible, is that in this way, the L that we get is going to be a model of set theory. And the thing that we're going to be doing can be done completely within set theory without quantifying over formulas. Anyway, so this is a typical definable set. Yeah.
Sorry, perhaps naive question. What's the problem with quantifying over formula?
You can't.
Why not?
They are not members of, they are not sets.
Okay, let's go.
Yeah, this is actually on the meta level. We're saying from the outside, okay, that set looks definable because I can find a formula and a few points in M that does this. So right now, yeah, that's a good. We're looking at V from the outside, and we're describing how you might want to call something definable or not. And this is a pretty decent way of saying definable. And so now you can, I did this for set theory, but this can be done for any language. So the unit element of a group, the neutral element of a group, is definable because it's the only one that when you multiply by it, nothing happens. And you can write that down in a sentence, and that defines that member of the group. The inverse of a member is definable over the group and that element that you're using. So that, you know, the function, say, that assigns to everything its inverse is a definable function because you can write down. And that's about it for group theory, because all the other things tend to use stuff outside the group. Like the order uses natural numbers and all kinds of other things. Okay, abelian, that is completely inside the group. So this is...
It's not internal. That's our problem. And
Yeah.
that's the...
Yeah, right now it's on the meta level, but what we want to do is completely in the theory, and that's going to take some time. So we have defined relativation and we have defined more or less definability. Okay, now the cat's already out of the bag. This is not a good definition, but we're going to run with it anyway for a while. M is definable without parameters, by the way, even. Using what formula?
Being element of.
And of course we can take away the M because we didn't do anything.
Does this assume transitivity?
Yet another point. That's why transitive sets are so popular. You get this. This equality need not hold. Especially if X is one of those epsilon minimal elements of M, and this is empty and this potentially not. If M is transitive, yes. So if you have a transitive set, then at least there is something in the definable family. Okay, we knew this was in the definable family, but you could be very unlucky and that could be everything. But if the set is transitive, you have some luck, you get M at least back in there. And of course, no matter what, the definable sets form a subfamily of the power set. We need to make that clear as well. Now, pardon?
Is that inclusion proper?
What do you think?
I'd say, intuitively I'd say yeah, but I assume that's very hard to do.
Yeah, because how many formulas are there in set theory?
Countably many.
So what if M is countable? How many definable subsets are there?
At most, countably many.
We have countably many tuples, we have countably many formulas, so we only have countably many expressions like this. That's going to be one of the things that we'll be using in that computation that said the cardinality of L alpha was the same as the cardinality of alpha, if alpha was infinite. That hinges on the fact that the language of set theory is countable, and that, of course, a countable set has only countably many tuples, and as we know, when we apply choice, every infinite set has as many infinite sets as elements. So under AC, that computation is done. What computation is done? Well, after we've defined L alpha, because now you can, but I want to say then, if M is transitive, then so is this definable thing. Why is that? Well, every member of M is a subset of M. And every other member of def is a subset of M too. So whenever I take an element of a member of def M, I have a member of M, so there. Which is useful to know, because now we're going to build our hierarchy. Let's see, did I? Yep, okay. So if we use this, Because okay, we already know that L alpha is going to be a member of L alpha plus 1 because M was always a member of the definable family. But since we're using the fact that I just erased by induction, it follows that all the L alphas are transitive. So then also L alpha is a subset of L alpha plus 1, but we checked that too for the transitive sets. And what are the ordinals in L alpha? Those are the ordinals below alpha. Again, by induction, we have to check alpha 0, clear, because empty is empty is empty is empty. If we have a limit, then the unions on both sides will give us the result. So we already have this. All we need to show is that beta is actually a member of this and nothing more. Now that's a little bit we know this.
Can you say transitive and well ordered by inclusion? Does that suffice to be an ordinal?
Yeah, that's the definition.
Fair enough. And that's just a formula, right?
Yeah, but
Really, Rx in L beta?
right. That doesn't make it any easier, by the way, but if this is true, then this is true. Because this simply talks about all subsets of X, regardless of whether they're in L beta. This talks about all subsets of X that are in L beta. So if this is true, then we might not get this. So this is a subset of that. But is this a subset of that? Remember, we are using the axiom of foundation. And I seem to remember that when I introduced the axiom of foundation, I said something about, but now being an ordinal is easier. 2 points, 1 point is the score so far. Yeah.
I think I deserve some extra.
X is an ordinal means X is transitive and linearly ordered by the element of relation. And when you write that formula and you stick in the M's, nothing changes. Or you stick in the L beta, nothing changes because of transitivity. Being an ordinal, now that we have the axiom of foundation, only depends on the members and their mutual relations. It doesn't depend on subsets anymore. Well, there you have it. I'll get back to this later because this is going to be this type of argument is going to be an important point later on. The way we describe certain things is important. Sometimes the old definition is not suitable for our purposes. We need a characterization, but that also means that the L betas or the M's that we'll be talking about need to be sometimes sufficiently rich. So yes, because of the linear order thing, these two are the same. So beta is a member of L beta plus 1. But alpha itself is not even a member of the power set of L beta. It's not a subset of L beta at all. So beta is a member of L beta plus 1, alpha is not, so that's, by transitivity, if some larger ordinal would still be in L beta, alpha would be there, but it isn't. So we know a few things about our L's. Do we know enough, for example, to know that we're talking about, well, for one thing, the L alphas, they try to keep up with the V's. Occasionally they succeed and are equal, but most of the time they lag behind desperately. This is a nice exercise in working with these formulas. The empty set is a member of L alpha plus 1. Well, it's a member of L alpha. It's a member of L1, but okay, so that's fine. Suppose we have proven that an initial segment of our F is already in L alpha plus 1. So if I is 0, then we have nothing, then it's just the empty set that's being a member of L alpha plus 1. Now, if we calculate the image of this, then of course we get the image of the initial segment plus this singleton thing. Now, this is an L alpha plus 1 by inductive assumption, and of course if I is equal to 0, then this is nothing, and all we're talking about is this. Well, the singleton set, we can write down what it is. This. So it's a member of, keep talking about M's, because this actually works for many transitive M's as well. So fine. And we can just write it like so. By induction, we have a formula that gives us the elements of this by assumption. So, okay, that's the formula with possible parameters, but let's not clutter the thing. So this will tell you you're either fulfilling this formula, in which case you're there, or you're fulfilling this formula, in which case you're there. So by induction, you prove that every initial segment, so in the end, now the reason I did it like so is because of the thing I did a few weeks ago when we were talking about all those natural numbers with those corners around them. Those were the copies of the real meta-natural numbers in the theory. Now, if you knew that only the real copies of the meta-natural numbers were the natural numbers, then we could have done simply x is equal to x1 or x is equal to x2 or x is equal to xn. But if we have one of those non-standard natural numbers, then that's not going to fly. And then we have to do this inductive bit. Okay, it's almost where did I put the eraser? In the obvious place, of course. So now you can prove relatively easily that Ln is equal to Vn for every natural number n, because the finite subsets are, all you do is add finite subsets. L omega is V omega. And this is the place where they start to diverge, because this, as we will see, is countable, and this is uncountable. Okay, we already indicated why this is the case, because you use AC to count we count the formulas on the meta level, and we count the tuples using AC, and then we get as many things as there are in alpha every time. And you need to start at omega, of course, because this is not true for natural numbers. V omega is something like 2 to the 2 to the 2 to the n. Vn is 2 to the 2 to the n big, or something like that. So, but As we shall see, when we do the definability proper, this will be a theorem without choice, because we can effectively enumerate L alpha. Well, that's a great moment to have a break, because after the break, we'll see that we have a model of ZF. Almost.